Okay. So yes, I'm Avik. I work at Facebook on languages and compilers and such things. I'm going to talk about some exciting stuff we have been doing around static type checking for JavaScript for around the past couple of years or so. So why are we doing this? One line summary is that we really like JavaScript. No matter what people say about JavaScript, it really works well for us. It's really good at the things that it does. Basically, it has these three qualities that we really value at Facebook, which is it runs fast, but also developing in it is pretty fast. You can try out things and you can see them in real time on the browser. If you don't like something, you can edit it and then run basically refresh the browser and you see the results immediately. So that kind of fosters some kind of creativity and inspiration. That kind of fast edit run cycle really changes how you develop code. It's also pretty expressive. You can write quick prototypes in it, but also it has a fairly rich kind of functional paradigm built into it. It has lots of reflection features, so you can build lots of abstractions and frameworks in JavaScript for use by other JavaScript code. And it runs everywhere, so anything you write has universal reach. So that's pretty good as well. So all of this makes JavaScript a pretty good language to build rich experiences in. However, it is severely underpowered in some areas that really start to hurt as your code base grows. So you guys must be familiar with all of these things. So obviously, like maintainability becomes a nightmare because nobody knows what the contracts are, and if you put thousands of developers in an environment where they are constantly banging on the same code base and they're making edits and pushing code live, you really need some sort of discipline across these developers on what the contracts are. What they can assume, what they must guarantee for other things, for other developers, so that not to break the site. So essentially, what's missing is all the good things that you get, for example, in other languages like Java, which are statically typed, which supports programming in the large. So types are the obvious answer to this question. So theoretically, you would think yes, adding types would actually help us, but also we have some experience in this problem. At some point, as you might know, most of our website is written in PHP, and at some point, all of that was in raw PHP, and then we had this project called Hack, which added a layer of static typing onto PHP, and now most of our PHP has been converted to Hack. And that has helped immensely. Like anecdotal evidence is that like most of our developers really like Hack, and they really enjoyed this move, and it had made our code much better, much more maintainable. It has fixed lots of bugs. It has also caught lots of bugs before they went live into production. So it's worked pretty nice for us. So obviously we want to do the same thing. We wanted to do the same thing for JavaScript. And a couple of years ago, we basically had this design question. Okay, we want types for JavaScript. Can we really throw any type system that we want at JavaScript? So that would be pretty naive. So we had to actually think about this. There are some constraints that we had to deal with. One is, remember I told you that developing in JavaScript is pretty fast, and JavaScript is a pretty expressive language, right? We don't want to kill any of that. So first thing we don't want to kill is the spontaneity of this fast edit run cycle. We want to keep this more or less untouched. So that immediately means that you cannot have any lengthy compile time delays. And we're not talking about a small code base here. We're talking about millions and millions of lines of code. You really can't like make a small change and then run your compiler and take a coffee break and come back and then start coding again. That would immediately kill off half of the advantages of using JavaScript in the first place. Another thing you cannot do is try to design a very sane subset of JavaScript, where sane is in your head, right? It's tempered by your biases about language design and so on. you can't really do that. JavaScript is a language for a lot of people. A lot of people see a lot of value in different parts of the language. You don't really want to design a arbitrary different subset of the language. And that would actually make your life easier as a type system designer, but you simply can't do that because you'll alienate developers and they won't use your type system anymore. We didn't want to do that. We wanted to build something that would work for everybody. So the pithy way to say this is that we want to maximize value and we minimize overhead. Where value is, we want to catch as many type errors as possible before the code goes live into production. But also we want to minimize the overhead. And overhead comes from slowing down your developer experience. It comes from restricting you in arbitrary ways. It also comes to some extent in writing down type annotations and so on. So we'll see some of that. There's always a trade-off to be made there. So what we wanted was some kind of scalable but powerful type inference engine that we could throw at JavaScript. And the thing that's going to drive this type inference is flow analysis, and that kind of gives us the name of this tool, which we call flow. So it's a type checker for JavaScript. Its main aim is to address some of these shortcomings of JavaScript, namely how to program in the large with JavaScript without ruining any of its good parts. And in this talk, I'll describe most of its features, some of its implementation, and so on. I won't tell you everything about everything that there is to know about Flow. There's simply not enough time. But I'll give you enough links at the end of the talk so that you can go and explore Flow on your own as well. I should tell at this point that Flow is open source. It was open sourced almost a year back now. There's a pretty thriving community that is building around Flow externally, and internally we are using Flow a lot at Facebook. Internal adoption has been growing pretty exponentially. So we are pretty happy with the way things are, but obviously it's still an ongoing project, and there's a lot of work to be done. So I would encourage all of you to kind of participate in this thing, because we think that this is the right way to type JavaScript. Okay, so let me go into the type system features a little bit and show you why we think Flow does well when it tries to preserve the expressiveness of JavaScript, and it tries to understand what's going on when you're writing JavaScript. So let me start off with a very simple example. Here's a function that computes the area given a radius. Obviously, it's expecting a number, and it returns a number, and it's being called with a string. Right? So if you know JavaScript to some extent, you would think that the string would be auto converted to a number and things might go fine. But trust me, things won't go fine. I've actually inserted an O instead of a 0 here, so it's not going to work as you expect. But more generally, you cannot rely on arbitrary type coercions in JavaScript. Just the specification of this coercion function takes 2 pages or more in the specification, and it's simply the biggest source of bugs that people face. And to a type system designer, this is immediately an error. So interests are not they are completely aligned in this case. This should be an error. So what you need to do for Flow to catch this error is to add a header with @flow on it, and that's it. You don't need to do anything else. You will see this error in your code. So 2 things to note here. This is a very trivial example, but 2 things to note here is that Flow is opt-in. So it does not look at your code unless you tell it to look at your code. And this works beautifully because initially you would have millions of lines of code that Flow has no knowledge about. And if you tried to run Flow on all of that code, you would get millions and millions of type errors that developers would have no idea where to begin and how to fix those errors, right? So what you do is you very gradually bring your code into this flows world, and it will start building information about your code. The second thing is you really didn't need any annotations, and you might think that this code is pretty simple, and obviously I won't need annotations, but there are type checkers out there for JavaScript, for example, TypeScript, that would need an annotation, otherwise it would not catch this error, right? So there's kind of philosophical difference between Flow and these other type checkers, in that we believe that most people who are coding in JavaScript actually have typed invariants in their head, and they don't want to write them down. So we are in the business of inferring those invariants, whereas other type checkers would take a more pessimistic view, and they would think that most code is dynamically typed and untypable, and therefore we should type only when you actually specify type annotations, right? So those are the small points I wanted to make in this piece of code. Let's look at a slightly yes.
About the last example, if this code were to run, what would the runtime error look like? Would it be a lot more difficult to debug than the type error message?
Yes, I think so. Here it's pretty clear that a string is being passed where a number is being expected, and the way Flow figures that out is that it knows that multiplication works for numbers, and if it gets anything other than a number, it tries to convert it to a number. And in this case, at runtime, what would happen is this would get converted to not a number, and you would get basically not a number out of that function. And maybe you were clever enough to kind of handle it in one case, but that thing might propagate, because anywhere not number goes, it creates even more not a numbers. So yeah, eventually I predict you would get a crash, and it would be far off from where you expected. So it would be much harder to debug, yes. So let's look at a slightly less trivial example. So this is a function that takes an input, maybe it's a string or something, and it returns its length. And you're passing null to this function. So this, in our world, would also be an error. So this goes back to basically some decision that was taken in the 60s about null being part of every type, which we don't believe in, and the original creator of that design also disagrees with it right now, very famously so. He calls it a billion-dollar mistake. So this is also a type error in Flow. Okay, so we do not consider null to be part of every type. If you do want it, you can have it by saying that I want null as well as string, but here it's pretty clear that if you try to do a dot length on null, it will result in a runtime error. So we try to catch that at compile time. What's even cooler is that so what's a typical fix for this kind of thing, right? You add a null check. You say if input is not equal to null, then access length property. Otherwise, return something that's acts like the default or something, right? And this code actually type checks. So if you throw this code at Flow, it would understand that even though null might be coming in, it would fail to pass this dynamic check. Therefore, this part of the code will not be touched by any input that is null. So it's actually safe. And you can codify this by adding annotations. So let me talk about annotations a little bit. So this question mark string that you see is denoting the expectation that the input is not only string, but it could be nullable. So it could also have null in the set of values that it denotes. And the output is annotated as number. And it's easy enough for Flow to kind of prove that if the input is nullable string, then the output is always number, because in this case, the output would be number. In this case, it would be number 2. And I've been talking about type annotations not being required for flow, but it is required in one place. And the reason for that will be clear later on in the talk as I talk about scalability and so on. So what we require is that if you, well, let me back up and say that if you're going to write millions of lines of code of JavaScript, you better break it up into files, right? And that's not a new idea. Every JavaScript developer knows that, and there are very explicit module systems. Well, earlier there were kind of de facto module systems. Now there is a formal module system for JavaScript, and you are expected to code in this fashion, where you write small files that are self-contained modules and they export stuff. And other files can include your modules, and they can interact with your modules only through the things that you export. Everything else is guaranteed to be private, or at least privately scoped. So what we require is that when you're trying to export something, you annotate it. And again, it helps us for other reasons that I'll go into later. But it also aligns perfectly with what any sane developer would do, because you are what your module exports, right? And other people would interact with your module through your export. So you should, as a matter of documentation, write down some types so that other callers don't have to look at your code to understand what your function is doing. So in this case, you are exporting this size function, and you're annotating it with what its input and output types are. And then other code can use your function. It knows that it's safe to call it with null because the type is nullable string. So you've separately proved that this code is safe under those assumptions, so that all callers are actually safe as long as they satisfy your types, your type signatures. So with type annotations in hand, you can do even more cooler things. So I'm trying to combine all the concepts that we saw in the previous few slides in this very kind of surprising code that is actually pretty common. It's a common idiom in JavaScript. If you're familiar with ML or other functional programming languages, you're familiar with these abstract data types that you write all the time, right? Which are defined by cases, and every case has something like a constructor and then a differently typed payload, right? So, for example, a binary tree could be of two kinds. It could be a leaf that has a value field, or it could be a branch that has two fields left and right, right? Now in JavaScript, what people do is actually encode these things as objects, and they have one special field. They won't tell you what field it is, but they would know in their head that there is a field called kind that would house the constructor name as a string. And then the rest of the rest of the object would have a different shape based on exactly what the value of this string is. And you would see code like this, which corresponds to ML pattern matching, which basically does a switch on the tree.kind. And if it's a leaf, it does something, and it expects that objects of the shape that it would expect if that kind thing was leaf. Otherwise, it would expect some other properties to exist on that object. Okay. So if you throw this at Flow, Flow would actually understand this idiom as well. And it's a combination of all the things that you saw earlier. It knows how to refine types based on dynamic checks, and all you're doing is a dynamic check saying that tree.kind is triple equal to leaf here. And it can narrow down these cases. So just like a nullable string is really a union type, it's null or string. You can have other kinds of unions. This is a union type between two object shapes, and it knows how to narrow down these unions to specific cases based on dynamic checks. Okay, so this kind of idiom is very useful. There's a library that we open sourced called GraphQL that is pretty popular that uses this idiom a lot. We also use this idiom in something called Flux that is used for dispatching actions and so on. So again, you find this pattern a lot out in the wild. So this kind of confirms two things. One is developers actually write pretty well-typed code, even though your type system may not be powerful enough to understand it. And we try to be powerful enough to understand it in this case. But also JavaScript is a functional language. It's not that bad, right? You can obviously write insane code in JavaScript, and it's our job to kind of ban such code. But other people actually write pretty disciplined code. Okay, so zooming out a little bit, what we're trying to do here is that we were talking about expressiveness, right? So imagine a code base that is written in JavaScript, has no knowledge of types, so it's obviously as maximally expressive as it can be. And now we are trying to throw a type checker at this code. And if you threw a traditional type checker at this JavaScript, then we think that part of it would be easily typed. But then a large chunk would have to be rewritten to kind of satisfy the type checker. And this is kind of thought to be a kind of expected cost of adding a type system to a language. But then there would be other things that your type system just doesn't reason about, for example, nullability. So there would still be a lot of unsafe code there that your type checker would say it's fine, but it's not fine because there would be runtime errors if you ran that code. So basically our mission, it's obviously exaggerated to some extent, but our mission is to extend the easily typed part to as much as possible, and minimize the parts that have to be rewritten to kind of satisfy the type checker, and also minimize the amount of unsafe code that you're writing. So that's the goal anyway. And beyond type checking, there's another ulterior motive to adding types to a large code base. And we are only beginning to explore this a little bit at Facebook right now. Is that once you have an kind of an error-free part of your code base, you can actually use it for a lot of code intelligence. So we have these editors through which you are writing code, right? And the way you interact with your code is not just you're looking for type errors, and if there are no type errors, you're happy. You're actually like trying to do autocomplete, and you are trying to find out the type of a function so that you can pass in the right kinds of arguments. So you are basically interacting with this type checker a lot, and you are trying to get information about your code through your editor. So all of that is also powered by type checking, right? So when the type checker says there are no errors, it's not that it kind of throws away all of the information, or it shouldn't throw away all of the information it used to kind of infer that. It can keep that information around and present it back to the user in lots of useful ways. So we are trying to do some of that as well. All right, so enough about expressivity. All of this would be useless if we did not satisfy the first constraint that we said we had to satisfy, which is don't kill the spontaneity of what the developer experience feels like, right? So we want type checking to be extremely fast, otherwise it would not work. Like nobody would use this thing. So the way you solve this problem is by a very simple and kind of, I would say, well-known idea, but people don't use it as much, is that you push type checking to the background. There's always a persistent server that knows about your code base, and it knows about all the type errors that are. It knows about what uses point to what definitions. It knows everything that it needs to know, and then tools would just make queries on this code base on this server. So type checking is pretty proactive in this model. So if things change, if some files change, if you're editing some files and you save them, or you rebase and suddenly a huge set of files come into your file system and a huge set of files get deleted or moved and so on, the server has to proactively pick up these changes and re-enter a stable state where it knows again everything about your code base, right? And it has to keep itself up to date very fast. Otherwise, you'll notice that something is happening. But think of it from the user's perspective. The user, it looks for some type errors, and he happily codes for a while, and then he saves the changes, and then a second later or something, it looks for type errors again. In that 1 second, there was no explicit command telling the type checker to kind of recompile the whole code base. The type checker has already done it. As soon as you save the file, it has done what it needed to do. So this is basically the model, and obviously this will work only if you're doing incremental analysis. You cannot hope to retype check all of your millions of lines of code on every small save. So that's where all the intelligence comes in. You have to design your type system or your type checker to break up the information that it gathers from individual files and keep them around in modular fashion so that they can be recombined in opportunistic ways. As soon as something changes in your code base, you would only recheck the files that need to be rechecked, essentially, and not everything else. And moreover, everything is all of this implementation is highly parallelized. So there are multiple stages of the type checker, and I'll go into some of these phases later on in the talk. All of these phases are highly parallelized to make maximum use of the cores of your machine. Okay. And again, this is very useful for us because again, millions of lines of code bases. We actually do most of our developers on pretty strong machines that have lots of parallelism. But if you're on a smaller code base and you still have 8 cores, this thing will still run pretty fast. So I should say that most of this part of the systems part, implementation part of Flow is actually borrowed from Hack. Hack is this other language that we built. And yeah, it shares most of this infrastructure from there. So before we kind of go deeper into Flow, I want to say that there are lots of things that we won't cover in this talk. There are lots of features that we won't talk about. So ES6 is the latest version of JavaScript, but then there's going to be a ES7 next year and so on. There are lots of new features. So JavaScript itself is kind of a moving and evolving language. So there are lots of new features like classes and arrow functions and const, destructuring for pattern matching. There's async await for asynchronous programming. Modules are talked about. There are other ways in which you can write, you can take different number of arguments and functions and so on. So all of those features are implemented in Flow. So basically, you don't have to wait for browsers to kind of implement this new language. You can already start coding in this newer variant of the language, and there are lots of like transpilers. The one we use is called Babel, which transpiles this newer form of the language to a form that is, say, ES5, that is understood by most browsers today. Okay, so your coding, your surface level coding, doesn't have to wait for browsers to catch up. You can already use these features, and you can use Flow in conjunction with these features. And also driving all of this is a deep understanding of JavaScript internals. So there are lots of foundational building blocks in JavaScript. For example, there are these objects that are extensible. They're dynamic maps, and you can add properties to them. There are prototypes that implement some sort of inheritance hierarchy. There are open methods that basically can bind to any receiver as they want. So you have every function takes an implicit extra parameter called this, and if you attach that function to an arbitrary object and you call that function as a method through that object will be bound to the this of that function. So things like that, right? So these are pretty powerful concepts, and these are things that enable things like classes to be built on top of these features, but also other kinds of frameworks. So for Flow to understand these low-level features is very, very important, because then it can model the higher-level features as basically downcodings to these smaller concepts. And there are other things like as well. For example, arrays are used as tuples in JavaScript. I just talked about disjoint unions. We need generics, pretty powerful generics to express some of these sort of types for these powerful frameworks and abstractions that are built in JavaScript. So all of this is there. But I won't go into too much detail into these advanced features. So let me give you just a taste of how the type checker itself runs. Okay. So the traditional view of a type is that it describes the values that an expression might take at runtime. So to a first approximation, a type is a set of values, really. So if you say number, you mean the set of all numbers. So if you're typing a certain variable as number, you expect the set of value, possibly like numbers to flow into this variable. Okay. But there is another view of type that you can add to this notion, which is you can also describe operations that you want to allow on these values. And for us, like a type could be either one of these. If it describes a set of values, we call it def types. If it describes a use of this value, we call it a use type. And you can say, for example, that things that you're familiar with in your language, like functions and objects and arrays, classes, things that you can actually think of as values, these are described by def types. But corresponding operations on these values, like function calls or property accesses or element accesses or instantiations of classes, dynamic tests on expressions, all of these operations that you kind of write to glue together these values in your code, these are also types, and these are what we call use types. So type checking involves two things. One, the first step is you take your program and you transform your program to a set of constraints that constrain these def types to use types. So basically, you're looking at every operation in your program, and you're saying, okay, I'm trying to do this operation on this set of values. So let me generate a constraint that describes that, and I will see if this operation makes sense or not. Okay, and if it doesn't make sense, that's a type error. So in this model, all you have is just these pairs of def types going to use types, and that's the information you feed into your type checker, essentially. So if everything goes well in your program, you should only see functions flowing to calls, and you should only see objects flowing to property accesses and so on. If you don't get this, then you basically have a type error. And this goes back to a very familiar idea in type checking called subtyping. So subtyping basically relates to like pairs of types that you can think of one type flowing to the other. So we basically generalize that notion, and we describe behaviors of programs this way. And again, none of this is new. I'll give you enough references to kind of recall where these ideas originated. Now you wanted to type inference, so you can generate type variables that denote things that are unknown at some point, and you can use this constraint system to infer types, infer solutions for these type variables. So there's nothing that I want to add to this model to describe that, except that you represent these type variables in terms of lower bounds and upper bounds. So these constraints that describe flows between different sets of things, they lead to constraints of this form ultimately, where a type variable has a set of lower bounds that describe the values that might be flowing into the particular location that is described by that type variable. And then there would be uses of that location that would be captured by a set of use types. And if you like type theory or logic, you can think of this set of types as describing a union of values that are flowing into that location, and this describing an intersection of uses that are emanating from that type variable. So what this model essentially gives you is that every value should satisfy every use that you have recorded here. Okay, so that's where the union and intersection interpretations come from. So just a matter of distinction, this is not HM's like Hindley-Mendler style inference. Hindley-Mendler style inference basically deals with unifying variables with particular types. Here we are keeping, instead of keeping the exact types that a variable unifies to, we are keeping lower bounds and upper bounds that constrain that solution. Okay, so it's more of a subset style analysis. And so Francois Potier's thesis describes how to like design an inference system that has basically a core representation of this form. And Flanagan's thesis deals with this distinction between def types and use types as more or less constraints that you generated to describe behaviors of a program. Okay, so just to give you a small example and to relate this back to subtyping, here's one rule that we have in our type system that should look completely familiar to you if you understand subtyping for functions. So a function type is nothing but a type that takes params and has a return type, and a call type is takes some types of arguments, and you don't know what the result type is. So you have a type variable that denotes the result types here. And this simplifies to args flowing to the param types and the return type flowing to the result. Okay. So again, this looks exactly like the subtyping rule for function types, except that in our heads we are interpreting the left-hand side as a set of values and the right-hand side as an operation. And the reason for this interpretation is not to like complicate this rule, but to allow you to model other kinds of operations that you want in your program as well. So that kind of frees your mind and allows you to generalize this rule to other scenarios as well. Okay, let me go into locals a little bit. So when you're in a local scope and you're doing a dynamic check, we want to refine the types of locals. Okay, so locals are modeled as having a specific type and an approximate type, and the relation between the specific type and the approximate type is exactly the same flow relation that I talked about in the previous slide. What's more, when you're thinking about refining types based on dynamic checks, you need to come out of these conditional blocks and kind of merge your environments as well. And those can also be modeled by subtypic constraints. So you can think of taking the union of what comes through an then branch and an else branch as basically, you have a new type variable that can take the union of the left-hand side and the right-hand side. And as I described, sets of def types are unions. So you can basically set up your constraints to not even mention the union. You can just say that both the then branch and the else branch flow to this new type variable that describes the join of that type. So this is how more or less we model flow sensitivity. We have this more specific type and an approximate type. The specific type can keep narrowing as you're doing dynamic checks. Sometimes you need to fall back to the approximate type when you're dealing with try-catch statements or points in your program where you don't know where you came from. You have to basically fall back to this approximate type. But other than that, you can be fairly flow sensitive in this model. Flow sensitivity is mostly limited to locals, although we do have some limited forms of heap sensitivity, which means that if you're doing a check on an object property, it's hard for us to track whether that check is still valid at a particular use later on in your program, because objects can be aliased and there could be so many other things that could be going on. So even if you have one function call in the middle of the check and the use, that function call could be invalidating the check that you just did. So this has to be necessarily limited in some forms, but for locals we do fine. Let me go into the architecture a little bit. So broadly, there are three phases of type checking. There's parsing, which is the simplest thing we can do. Although I should mention that we actually have now a parser for JavaScript that you can use, and this whole implementation is in ML. So if you're hacking an ML on a JavaScript project, you can use that parser in a pretty standalone fashion. So that's pretty useful already. But then we have these two other type checking phases, which we call infer and merge. The first phase does local type checking, which means that it looks at a file in isolation and then merge combines the information that you glean from individual files to get cross-module errors. Each of these phases are highly parallelized. So parsing is like embarrassingly parallel. You can parse every file in parallel logically. You're only limited by the number of cores you have. The local type checking is also embarrassingly parallel. You can do local type inference for every file in parallel. Merge used to be done in a different way. We used to, as of a couple of months back, maybe just a month back, we used to do this merge process completely parallelly, once for every file. But imagine that if your dependency graph between your modules is actually a graph that is sharing stuff, what the other module would do is they would re-merge the same files over and over again in parallel, and that worked for a while when we had a smaller number of files to deal with. But things stopped scaling at this point, so we have moved to this other model where we do a topological sort of the dependencies, and we do things at a particular level, if you will, at a time, and other jobs have to wait for the dependencies to be done before they can be discharged. So this is still a very parallel operation, but it's based on a dynamic work list that is not known when you're starting off. You don't know how this work list is going to be generated. Some number of files finish, and then they unblock other files and so on. So this the local phase works as follows. You have a module with a bunch of imports and an export, and we replace the imports and exports with unknowns. Unknowns, again, in our world are just type variables. And internally, we generate constraints. And these constraints would work for any imports and exports that you want. So this is basically a very local type check. It doesn't know anything about other things in the world. But the constraints would always work given those unknowns that are at the boundaries of the file. And in the next phase, imagine somehow you have converted the exports to these annotations that we were requiring at module boundaries, and you reprocess the constraints based on those annotations. And now what you get is a system of equations that are describing those annotations. And this you can feed back into the merge process again in the previous slide, right? So this is how you kind of combine information, local information from every file to get cross-module information about across your code base. So I mentioned 3 big phases in type checking, but there are actually many other tasks as well that are going on all the time. And from experience, I can tell you that no task is big enough to not parallelize, right? So at the scale at which we work, even helper tasks like module resolution or dependency calculation, all of these can be parallelized. There's opportunities to parallelize everywhere. Anytime you have an operation, you try to think of it as how do I break it up so that I can combine at the end information that is generated from individual files at a time. For big things that you are inputting and outputting, we have this thing called shared memory. This is also an implementation that comes from Hack, and it's totally awesome. We use that all the time. Basically, parallel workers can communicate through the shared memory instead of serializing and deserializing big chunks of data. For small things, you can actually still use serialization. But for all the bigger things, for example, after the parse phase, we store the ASTs in shared memory so that they can be used in later phases of type checking. We store the local type information as well at the end of the infer phase in the heap through as shared memory so that they can be used by the third phase. And every part that you're generating in the third phase is also put into the shared memory so that it can be used by later phases. Also, when you're incrementally updating stuff, you can basically reuse this information and retype check only a few files re-update your state, and you get to a stable state again. Okay, so let me close. Actually, I'm out of time, but I'm told that the next talk is cancelled, so I'll take 5 more minutes. These are some juicy limitations, opportunities that you can think of to work on Flow if you on your free time. So one is improving heap sensitivity. Okay, so nobody likes to only do dynamic checks on locals. This pattern is pretty common, where you do a check on an object property, and you call a function, and that function, you don't know whether that function could be updating o.x. So here you cannot assume that o.x is still null. Unfortunately, sometimes you have very benign functions that don't do anything. Or, I mean, this is a stylized example, but they have nothing to do with O at all. And it's hard to recognize when the effects of a function basically don't destroy your heap sensitivity. So there's a lot of work to be done in this area. For now, there are workarounds. You can store the o.x in an x. And this is basically one way of telling Flow that this function can never muck around with this variable. Okay, because we don't do Hindley-Miller type inference, in fact, it's impossible to do it because we are dealing with subtyping and generics at the same time, and the problem in general is undecidable. I mean, for the things that we want to do. We fail to type check programs like this, where you're writing a polymorphic function here, and you are calling it with different types, and we would basically conflate these call sites and throw type errors, which are spurious in this case. Again, there is a workaround. We do have generics as long as you explicitly provide these generics. We don't infer generics for you, but you can always say that app is a generic function, and then everything would work fine. Also, there are some pieces of code that do a lot of dynamic checks, but the dynamic checks are kind of correlated. So this function takes either 2 numbers or 2 strings, or does something else. And if you wanted to write this type down using just unions, you would get some imprecise types. So what you want is overloaded types, some form of intersection of function types. And again, there's a way to write down these types at this point, but we cannot infer them. So inferring them would be nice. Anyway, so let me say something about some ongoing challenges that we faced from day one and are still in the process of solving. We're not there yet. One is error reporting. This is like a well-known problem with constraint systems of the form that I described, where essentially you are trying to find inconsistencies between parts of a program that could be very far apart, and somewhere you find an inconsistency. You know that there is a type error, but you don't know exactly who to blame for the type error. And there are lots of heuristics you could use to blame, and that's basically what we were to toy with. So right now we are kind of in the process of improving. So our users tell us the way we do error reporting by localizing the errors a bit more, so that they are closer to the operation that was in place that when a type error was triggered. But there are other things we could do here. We're still in the process of exploring. For example, there's a paper by a student of Andrew Myers and that group. There's a series of papers that are using machine learning techniques to discover points to blame, basically by doing some kind of Bayesian analysis on which points of the program are participating in more error paths than successful paths. So maybe we can implement something like that to see if we get better results. Another thing that does not work in this system very well is backtracking. So this is a system where you keep adding constraints, and the whole system keeps getting more and more constrained. However, if you think about the implementation of union types, when you have to check whether a value belongs to a particular union type or not, you have to test for one branch, and if it does not succeed, then you have to backtrack and test the other thing. So that is not monotonic in the sense that this system was designed for more monotonic constraints and not really for testing these kinds of constraints. So so the way we do those checks are a complete hack at this point. They work some of the time, and we know when they don't work, and we try to warn users when they will not work, but it's not perfect. So we need a way to kind of implement backtracking in this system. All right, so to summarize, Flow is a scalable, powerful type inference engine for JavaScript. Most of its power comes from a deep understanding of JavaScript, and most of its scalability comes from a highly parallelized and modular incremental design. It's open source. There are lots of resources out there. There was the blog post that was that initially introduced Flow around a year back to the world. There's a website with examples and other links. Source code lives on GitHub. You can follow along on Twitter and IRC handles. But I want to basically encourage you to participate now, because there's a very sweet time in the evolution of JavaScript. So JavaScript is evolving very fast, the language itself, but also there are these type systems that have come back now into the limelight. There's TypeScript, and then there's Flow. We are still in the process of figuring out how best to type check JavaScript. There's a strong possibility that maybe JavaScript in the future might have some support, standard or not, for types that a lot of people agree with. We're trying to come up with the best possible design for that scenario. And this is if you participate in some of these projects, you'll basically be at the forefront of shaping how JavaScript for the future looks like. So Flow is a very active project. Internally, we are pushing for adoption, but externally as well, even without trying, we have lots of contributors. There are lots of open issues, for example. People like us, more or less. So please go ahead and contribute to Flow on GitHub. There are lots of things you could do. Also, if you're a student who is trying to experiment with new ideas on static analysis for JavaScript, feel free to use parts of Flow in your work. I told you about the parser, so there are not too many complete ML parser for JavaScript around. I'd love to talk to you if you have other ideas. Thanks.